Hey everyone, and welcome. What if I told you that every single time you search for something online, hit the back button on your browser, or scroll through your photos, you're actually using these really powerful classic computer science tools? Well, today, we're going to pull back the curtain on these hidden data structures that pretty much run our entire digital lives. I mean, really think about it for a second. You start typing CAR, and boom, your phone instantly suggests card or care. How on earth does it do that? Is it some kind of magic? A really, really lucky guess? Nope. That incredible speed is no accident. It's the result of some seriously clever engineering. And that, right there, is what we're here to unpack. These structures are basically the secret scaffolding of all modern software. They organize information in very specific ways that make our favorite apps feel super fast, totally responsive, and, incredibly smart. So let's start with the basics. Okay, so first up, let's get into the fundamentals. These are the real workhorses that bring some order to all the chaos of digital info. You're interacting with these things constantly, even if you don't realize it. It seems so simple, doesn't it? You click a link, then another, then you hit back, and you land exactly where you were before. But how does the browser remember that exact sequence so flawlessly every single time? While the secret is a neat little data structure called a stack. Just imagine a stack of plates at a buffet. The last web page you visited gets placed right on top. When you hit back, you just take that top plate off, revealing the one right underneath. Last one in is the first one out. Simple, elegant, and absolutely perfect for the job. But here's the catch, the trade-off. Adding to the top, which we call pushing, and taking from the top, popping, are unbelievably fast. We're talking constant time, or O of 1. The downside? You can't just reach in and grab a plate from the middle of the stack. It's built to do one specific thing and do it lightning fast, but that's it. So what happens when you do need to grab something from the middle? Like if you want to see photo number 500 in your gallery, you definitely don't want to have to flip through 499 other photos just to get there. You need instant access. And this is where the trusty Array comes in to save the day. Think of it like a long shelf with numbered slots. If you want what's in slot number 500, the computer just goes directly there. No fuss. This is called random access, and because it's also an O1 operation, it makes arrays the perfect tool for things like photo galleries. All right, so we've seen how stacks and arrays give us speed in different situations. Now let's get into the structures that were designed to solve one of the biggest challenges in all of computing: finding exactly what you need right now. I mean, if you had to search through an unsorted list of thousands of contacts one by one, you'd be there forever. But when you type a name into your phone, the result is just there. It's immediate. So how is that even possible? The answer is the incredibly powerful and versatile hash table. It uses a special function, a hash function, to turn a key, like the name Alice, into a specific address, like mailbox number 123. So instead of searching through everything, the computer just does a quick calculation and goes straight to the right spot. Now, you'll hear this a lot, especially if you're gearing up for a coding interview. It's a common simplification that gets repeated all the time about hash tables. But is it actually true? Not quite. And this is a really important distinction. The key here is that O of 1 is the average case. If your hash function isn't very good or the table gets too crowded, you can have multiple keys that end up at the same address. We call that a collision. And in the absolute worst case scenario, you're right back to searching a list one by one, which is a slow ON operation. Knowing that difference is crucial. Okay, so let's circle all the way back to our original mystery, that magical autocomplete. The secret weapon here is a really cool data structure called a trie, or a prefix tree. Imagine a big train station, where each letter you type sends a train down a very specific track. So after typing CAR, your train has arrived at a station where all the possible next words, like card and care, are just the next stops down the line. And here's the real magic. The time it takes to find those suggestions has nothing to do with how many words are in the dictionary. It only depends on the length of the word you're typing right now. And that is why it feels instantaneous, even if it's searching through millions of words. So now that we've got the fundamentals down, let's look at a couple of specialized structures that engineers use to solve some really complex, really big problems. So picture this. A service like Google wants to warn you if you're about to visit a malicious website.
How can they check if you've seen one specific URL before out of literally billions of possibilities without doing a slow, expensive database search every single time?
Well, they use this incredibly clever probabilistic tool called a Bloom filter. Think of it like a security panel with a big row of lights. When a new malicious URL is found, it's run through several different hash functions, and each function tells you which light to flip on. Later, when you visit a URL, you do the same process. If any of the lights it points to are still off, you know for sure it's not a known malicious URL. It's definitely safe. And here's the brilliant part. A Bloom filter uses almost no memory. It will never tell you a malicious site is safe. That's what we call zero false negatives. But because different URLs could accidentally light up the same set of lights, it might sometimes tell you a safe site is malicious, a false positive. For security, that's a trade-off you're happy to make. Better safe than sorry, right? So, as you can see, we've got this whole toolkit of really powerful structures. The real skill, the art of it, is knowing which secret weapon to pull out for the right job. Let's just quickly compare two we've already talked about. Do you need autocomplete or any kind of prefix search? The try is your champion, hands down. But if all you need is a super fast lookup for an exact key, like a user ID, and you want to be efficient with memory, a hash table is almost always going to be your best bet. And this idea applies to so many other problems. Like we saw, an undo button screams for a stack. If you need to find the shortest route in a GPS app, engineers use a graph to map out all the roads. And for something like scheduling tasks in your computer's operating system, they might use a heap to always know what the most important job is. See? Every problem has its perfect tool. So here's the main thing I want you to take away from all this. This isn't just some abstract, theoretical computer science stuff. These are the practical, fundamental building blocks that engineers use every single day to create that illusion of instant that we all expect from our software. When you get these, you really start to get how our digital world actually works. And honestly, we've only just scratched the surface here. By knowing the right tool for the job, you can build things that don't just work, but are truly efficient and elegant. So the only question left is, now that you've seen the toolkit, what problem are you going to go solve first? Thanks for digging into this with me.